if E1, E2 and so on to En are mutually disjoint with disjoint events. So we are having E1, E2 and so on to En. N mutually disjoint events with probability of Ei is not equal to 0. Means all Eis or all Eis, all the events exist and none of them is so all the events E1, E2, E3 and so on to En exist and Ei is not an empty set. Okay, because P of Ei is not equal to 0, Ei is not an empty set and they are not impossible events, right? That is what it is said. None of the Ei is impossible events. All the Eis exist. So you are having E1, E2 and so on to En or mutually disjoint events with P of Ei is not equal to 0. Then for any arbitrary event A which is a subset of union I equal to 1 to n Ei such that P of A is greater than 0, we have P of Ei given A. Okay, what it is? P of Ei into P of A given Ei divided by summation P of Ei into P of A given Ei I equal to 1, 2 and so on to n. What is given here is E1, E2 and so on to n are mutually disjoint events with P of Ei is not equal to 0. And that means none of the Ei is impossible event. Therefore, any arbitrary event A which is a subset of union, okay, I equal to 1 to n Ei such that P of A is not equal to P of A is greater than 0. And P of A is greater than 0 implies that again even A exists and it is also impossible event. We have P of Ei given A is P of Ei into P of A given Ei summation P of Ei into P of A given Ei. We will see this. For this first we will start the diagram. Okay. So we will just discuss about the diagram. What is this diagram? So we will have the sample space as proof. So we have the sample space as, we will consider this is the sample space. Okay, this is the sample space, yes. And we are having event E1, E2, okay, E3, somewhere you can keep E4, E5, E6, E7, E8, E9, like this it goes on and so on to En, right? Like that it goes. So we can call it as E1, this is E2, right? E3, see they are mutually disjoint events, okay? E3 we have already written now, E4, this is E4, okay? E4, E5, E6, E7, like that it goes on and on, right? E8, E9, E10, E11 and E12, like that it goes, right? S is a sample space which consists of E1, E2, all these events, there is no intersection, right? So they are mutually disjoint sets, right? Now we are going to consider one event A, some event A. Okay, this is my event A. What is this? Event A. A is subset of, from this figure it is very clear that A is nothing but A is subset of union I equal to 1 to n E I, some subset. So A is a subset of union I equal to 1 to n E I, right? So like that we are taking A. Now since A is subset of union I equal to 1 to n EI, we have what we have? A equal to, A can be taken as A intersection union I equal to 1 to n EI, right? Yes, what is given is A is subset, this red color one, red color circle we have drawn, no, that is nothing but our event A, right? What is a red color circle? It is our event A. That is A is subset of union I equal to 1 to n, some subset it is, right? That is A can be taken as A intersection all this union, right? Nothing harm in writing like this. Therefore, we have what we have? A can be written as A intersection union. Okay, what is union E1 E2? Like this you can write E1 union E2 union E3 union and so on union En. It goes on and so on to n. That is union, a union of all this set. No, E1 E2 E3 like this we can write, right? Because A is subset of we have written now, so A can be written as A intersection something. Okay, and this is nothing but using the De Morgan's distributive law. Okay, A intersection distributive law, A intersection E1, right? Union A intersection E2 union A intersection E3 union and so on A intersection En, right? So you can take this A intersection E1, then A intersection E2, like this you keep on writing. So A intersection E1 union, A intersection E1 union, A intersection E2 union and so on, right? And so on to A intersection En. Okay, this further you can write this as union. There are so many unions, right? Here union, union, union. So in general we can write union I equal to 1 to n. What are they? A intersection EIs, right? I varies from 1 to n. This we got it from the distributive law. Okay, simply by distributive law up to this we got. Okay, so if you just think about this A intersection E1. Okay, what about this set? Even A intersection E2, all these sets. That is nothing but subset of EI, right? Since A intersection EI, everything is nothing but subset of EI, right? We know this. I equal to 1 to and so on to n. What are they? They are mutually disjoint sets. Okay, mutually disjoint events. So A intersection EI, all these are mutually disjoint events. Moreover, they are subset of EI. Okay, we have by addition theorem. What this addition theorem says? Addition theorem of probability. Okay, we have by addition theorem of probability. What about all these events are mutually exclusive, right? See, if you, all this circle, green color circle I have drawn now, all these events are mutually exclusive, right? All these events are mutually exclusive, mutually disjoint we can say. This is also mutually disjoint. So all these events are mutually disjoint. Okay, mutually disjoint events. All these events are mutually disjoint. That is easily can be. If you see this inside the circle. So this part, A intersection EI. If I take particularly this part, suppose this part. Okay, this part and this part. Their intersection is null set, right? And same way, this part yellow color and green color, the intersection is null set. That's what I want to say, right? So A intersection EIs, these are all disjoint sets, mutually disjoint events. We have addition law of probability. Okay, what is P of A? P of A is nothing but probability of union I equal to 1 to n A intersection EI, right? Okay, so this can be written as, this is nothing but probability of A intersection E1 union A intersection E2, okay, union A intersection E3 union and so on, okay, union A intersection En, right? Union of all this, right? And this is nothing but they are mutually disjoint events. No, A intersection E1, A intersection E2, A intersection E3, they are mutually disjoint. So using the probability addition, so A intersection E1 you can separate it plus P of A intersection E2 plus and so on plus P of A intersection En, right? That is P of A can be written as summation I equal to 1 to n P of A intersection EI, right? And this can be written as summation I equal to 1 to n. What is P of A intersection EI? Okay, it is nothing but P of EI into P of A given EI. Okay, EI has already happened. So event A occurs after EI. So P of A given EI. This can be marked as equation 1. Right? This is what we got. By compound theorem of probability, by compound theorem of probability, on this compound theorem says P of A intersection EI, that is nothing but P of A into P of EI given A, right? That is nothing but P of A, okay, P of EI given A is nothing but, so you can others P of A can be taken to denominator, P of A intersection EI divided by P of A. Okay, what is P of EI given A? P of A intersection EI, okay, divided by P of A. And what is P of EI given A? Same thing. What is? That is nothing but P of A intersection EI, just now we have written now equation 2. You can mark it as equation 2. Okay, and 1 and 2. Okay, you use 1. Okay, E2. 2 says that this is nothing but P of A into P of EI given A. Okay, this is equation 2. Right? What is equation 1? This is what equation 1. Summation I equal to 1 to n. Summation I equal to 1 to n. P of EI into P of A given EI. This we got from here, right? P of EI into P of EI into P of A given EI, right? So, wait, P of A intersection EI, once again, oh, another way of writing also is there, that also we can write, because it is already there now, so no need to write that. Okay, and this can be, this is nothing but, another way of writing is, this is nothing but P of EI into P of A given EI, A given EI, right? We can mark it as equation 2. I'm using this part, so P of EI into P of A given EI. That's it. So we have proved the Bayes theorem, right? This is what we started and we proved the Bayes theorem.